All right, thank you so much. I'm Suren Byna from Lawrence Berkeley National Lab. We are located in Berkeley, United States. So I'll be talking about a project that we are involved for the last few years, more than 10 years now, in making HDF5 ready for exascale systems. As you may have seen in the top 500 list, we are now in the exascale era with Frontier system at Oak Ridge National Laboratory. And the XIO project is working with a couple of technologies, one HDF5, which everyone knows, and the other one is UniFi-FS. I'll briefly talk about the UniFi-FS, but mostly focus on HDF5 in this. Okay, let me see if I can. Okay, so kudos to the XIO team, which includes the HDF group, along with Argonne National Laboratory and multiple other national laboratories and universities. Several of the people that are on the team are also at the on location at ITER. So just to give a brief background, exascale computing project in the USA started about 7 years ago to focus on various applications that are of interest to US national problems and in the national security, energy security, economic security, scientific discovery, earth systems, and healthcare. And the overall, the project is divided into multiple sections. One of them is application development, which focuses on the 6 areas I mentioned, and the software technologies that focuses on the software stack to make all these applications run efficiently on exascale systems, and the hardware integration. The XIO project is part of the software technologies, mostly focusing on the IO technologies for exascale systems. And in the HDF5, we all know what it does. And the UniFi-FS is, in many of these systems that are coming up, there are storage technologies are included in each compute node, and there are thousands of these nodes. So to combine all those fast storage into a single file system or a namespace, UniFi-FS is being developed. So I will not talk more about that in this talk, but I'll focus on the HDF5. So HDF5 project mission XIO project is supporting applications and developing new features that make HDF5 ready for exascale architectures and tuning and maintenance of HDF5 capabilities that are already out there for large-scale systems. There are about 26 applications in the overall ECP, and out of those, and actually 26 applications, but more codes, nearly 45 codes or so. And 17 of them say HDF5 is critical for their success on the exascale systems. So to support that, we have been working with various applications and various engagements. I will not go across all the list, but I will talk about a few of them in the next few slides. So one of them is earthquake simulation, which is regional scale earthquake fault to structure simulations. And this application has been one of the applications that are running on full scale on these large scale systems. And they were using some kind of ASCII-based earthquake file formats before, but the number of files that they were using is huge in terms of tens of thousands of files. That wasn't very scalable for them, and it was taking too much time to read the input, so they wanted to convert to HDF5. So we helped them integrate HDF5 into their application. And with that, we achieved significantly better performance compared to those. For example, the initial USGS, the US Geographical Survey type of format that they were using initially, it was taking hundreds of seconds. but using HDF5 on burst buffers, which are the fast storage layers with HDF5, we could achieve less than a second, sub-second performance for them. And even when we use luster that they were using, so we do much better than and less than 100 seconds there too. And then we applied compression for them, and that improves the performance even further, and also reduces the amount of data that they have to store significantly. So this is from a recent run using 3,600 nodes on a Summit system called Summit, and using HDF5 gives very good performance for them, as well as good compression of their data. Such as the compression ratio was around 260 times. So they are very happy with that. And we also integrated HDF5 into a framework called AMREX, which is a block structured adaptive mesh refinement framework for solving PDEs on exascale architectures. And several applications in the exascale computing project use this framework. And a couple of them that we work with are called Nix and Castro, which simulate the astronomy object. And with their data, they were taking significantly large time, even with the HDF5 initial versions of the integration. And then we developed something called Asynchronous IO in a wall connector, which I'll talk a little bit later. But with that, we can hide much of the IO latency in those applications and achieve very good performance for them, such as these when we're storing about 385 gigabytes of data and the 5 time steps, we perform that within 25 to 30 seconds. Similarly, for Castro, which is produces about 559 gigabyte data per time step and 5 time steps, we do hide much of that IO latency as well, and less than 50 seconds is what it takes. So we are updating their file layouts a bit more further that can give better compression. So that is also ongoing work right now. And another simulation is a climate simulation model that uses NetCDF4 as the main interface for writing data to HDF5, but we noticed that there are significant performance bottlenecks in that approach because of the data that needs to be stored. It has to be canonical form, which is getting data from different places in memory and combining it and storing it into storage. That was causing a significantly worse performance. And then what we did was, instead of using NetCDF4, we use a direct HDF5 API. And then we also used a new API called Multi-Dataset API, which we are now integrating into HDF5 with the help of HDF group. That one achieves significantly better performance for different use cases. One of them is F-case, that's what they call. That gives about 15 to 30x better performance compared to the original HDF5. And it also improves the read performance to some extent, but not significantly compared to the write performance, because once it is written, read pattern is somewhat amenable to the canonical form that is being stored. So that is another application that we are working with. So based on all these applications, what we noticed is there are so many features in HDF5 that need to be tuned. And based on how we are tuning or choosing the configuration of HDF5, that the performance varies. So what we did is we took several of these IO kernels that are representative of the real parallel applications that run at large scale, and formed a benchmark suite called H5 Bench, and that can be used to tune HDF5 offline, and then apply those tuning parameters into real applications. So if anybody is interested in that benchmark suite, it is available here on the GitHub page. And with various features such as the synchronous, asynchronous is something that we continuously test. So that with the asynchronous, we do get very good write rate and read rate for various patterns. So in terms of the features that we have been developing, so one of them has been released. Many of you may already know the virtual object layer framework that is now available in HDF5. And based on the virtual object layer, we developed the asynchronous IO, caching and prefetching, and the GPIO, which is a virtual file driver, and then a couple of new things that we're developing as well. Okay, so the asynchronous IO, I think somebody was mentioning yesterday to develop or use a wall connector, so this is already available. This is useful when there is a phase of computation followed by IO or phase of IO followed by computation in read patterns. So if you are using a compute time and then a write time, compute time, write time, what we can do is move this write time into the asynchronous so that the compute doesn't have to wait. So, and the write happens in the background using background threads. And background threads are pretty much available in many of these exascale systems that we are using. So most of the write time can be hidden, except the last one, the last time step that has to be written, and after that there is no more compute time. So with that, we have tested, with that approach, we have tested on various systems, and asynchronous IO is very efficient. And when the asynchronous IO is 100% covered by computation time, we do get significantly better performance as shown here. And this has been integrated, as I mentioned, in the NX and Castro earlier. And then there is a system called FlashX, which is a code that simulates a large number of these star systems and all those explosions and all those. So that is also showing significantly better performance. For example, I show here the application speed up increases with the number of nodes that we are using. And this was an earlier result with only 7 nodes. Now we run it at a much larger scale at 128 nodes, and that overall performance increases even more. And some of the systems that are outside we are not directly working with are also starting to use this feature. So if anybody is interested in this feature in your applications, please let us know. You can, the code itself is available here, and it works with the latest release of HDF5. Another one is, as I mentioned, there are these node local storage available on various systems. So how do we use that to buffer the data or cache the data, and then write the data asynchronously in the background from those buffers to the actual file system? Or similarly, when reading the data, you read instead of just reading reading only the data that is being accessed, we can also prefetch more data into that buffer or the node local storage. Using that, we get significantly better performance there as well. So this is a simple test with a particle physics IO kernel, which shows 800 gigabytes per second at 256 nodes. And on a different system, when we use node local storage, the performance increases even further, which is close to, this is closer to a 1 terabyte per second performance, while the original HDF5 without this cache wall performs much worse because of the luster configuration there is and all this. So And we also tested this with AI applications that bring the data into node local storage and then access the data directly there instead of going to the a parallel file system that is much slower. So there also we see significantly better performance there. Okay, and that feature was also available in the HPC IO GitHub, so please feel free to check that out. There is another new feature that is recently developed in NVIDIA GPUs, is that instead of using the CPUs as a way to transfer the data, where CPU data goes from GPU to CPU and then written from the CPU, GPU direct storage is a new feature in NVIDIA systems and NVIDIA GPUs that can directly access the storage from GPUs. So we have developed a virtual file driver with the help of pluggable VFDs that HDF group developed, and that gives significantly better performance wherever we don't, instead of using this CPU memory directly access the data, directly move the data between GPU and storage. That gives good performance. And we have also tried that with multiple threads initiated on GPU and CPU writing that data or initiating that data to write the data or read the data from GPUs. So that is also available in this location. So if anybody is interested, please check that out. Similarly, we have also developed another tool that can give a good view of where the time is spent in I/O. So this is called DXD Explorer. So you may be aware that there is a tool called Darshan, which profiles the I/O data, and we have developed something called Darshan Extended Traces, which collects the each and every I/O call, and that is says how much data was done, how much where the data is written to. So we developed a visualizer of that, so that shows that can allow you to look into how much time each request is taking. And it is an interactive tool, so you can also see where the time is spent. For example, in this case, there is a long pause, or one call is taking, or one process is writing or doing something here. And that one, we analyze that it is a fill value problem. So one process is filling all these array, and that is unnecessary. So removing that reduces that much amount of time in that process. And if anybody is interested in looking at that, so it is also available on the HPC IO website. Okay, so this is a whirlwind of various tools that we have been developing. So I'll stop there. And basically, we support various exascale applications to use HDF5 efficiently. And we have been developing various features that make HDF5 ready for exascale computing. And in the process, we have also been developing some tools that can be used for general purpose, like H5 Bench, which is a parallel IO benchmark suite, and DXD Explorer. Okay, and yeah, I give the all the contacts, and thanks to various agencies that are helping here. All right, thank you.
Okay, thank you, Suren. Any questions for Suren? Here we go.
Nothing. I guess this will be like a offline follow-up to the question. So we do also have a GPFS file system, and I would like to try to reproduce these benchmarks. So could you share with me or point with me the exact configuration of the GPFS that you were using and the underlying hardware?
Yeah, so GPFS doesn't give a lot of control over what configuration we choose. So we didn't do anything specific there. So all we did was setting the alignment at HDF5 level, the alignment equal to the block size that GPFS uses. So in the system that we used on Summit system, that was 16 megabytes. So that's all we set at the HDF5 level. And all the other performance is exactly the same. And if you have any questions, please send me an email and I will point to exact codes.
Do you have a follow-up question? No, thank you. Any other questions? No? Let me check online if anybody online had a question. There's something in the chat. No, there aren't any questions online. Well then, thank you again, Suren.
All right, thank you.
We'll